Have you built a RAG system that works perfectly in testing? You ship it, real user, real question, something you know is in the knowledge base. The system says, I don't have any information about that. And then you go back and check. The document is there, the embedding is there, the chunk is there. Everything looks fine. That's the moment this video is about. Because everything looks fine is the most dangerous state a RAG system can be in. This happened to me. I built the knowledge base myself. I ingested those docs myself. I watched the job complete. And I still spent several hours debugging the wrong layer. It wasn't some exotic bug. It was a failure point that was always there. I just didn't know to look for it. That's what today's about. 7 layers, every failure point, every place your system can look completely healthy and still let your users down. So you don't have to learn this the hard way. Let's build this right. The first thing you need to understand about RAG systems is that most failures don't happen at retrieval. They happen here, at ingestion, before the data ever touches the embedded module. And the reason they are so hard to catch is that they are completely silent. The job finishes, no errors, chunk count looks reasonable, everything appears fine. But the foundation the entire system is working from has already been compromised. Here's what's actually happening when you ingest a PDF. PDFs aren't documents in the way we think about them. They are instructions for rendering pixels on a page. There is no native concept of a table, a heading, a row, or a column. It's all coordinates and drop commands. When a basic parser hits a table, it reads left to right, line by line, based on character position. Columns bleed into each other. Structure collapses into a string that carries none of the original meaning. In my case, the feature a user asked about was documented in a table. After ingestion, that table was garbled text. It got chunked, it got embedded, and when someone asked about it, the system searched a knowledge base that genuinely didn't contain the answer. Not because the document wasn't there, because the content had been destroyed before it's ever indexed. That's what we need to internalize about ingestion failures. The system isn't lying when it says it has no information. It genuinely doesn't. And the gap between what you believe is in the system and what actually is in the system is the most dangerous state a RAG architecture can be in. Production ingestion needs to do 4 things well. First, structure-aware extraction. Not just pulling text, but understanding document layout. Tables preserved as tables, headings recognized as headings, sections kept intact. 2, OCR with layout analysis for scan content. Not just character recognition, spatial understanding. 3rd, format normalization across everything you are ingesting. PDF, Word, HTML, email, whatever your sources are. 4th, metadata capture at ingestion time. Author version, access level, timestamp, not added later. Captured here where you still have the context to do it properly. The lesson here is this. Ingestion isn't file loading. It's meaning preservation. Every layer above this one is only as good as what layer this produces. Once you have structured data coming out of ingestion, the next question is how you break it apart for indexing. And this is the decision most engineers underestimate because it looks like a configuration choice, but it's actually an architectural one. Chunking defines the upper bound on retrieval quality, not the lower bound, the upper bound. Your embedded model, your retrieval strategy, your re-ranking logic, none of it can compensate for poor chunking. If you have fragmented meaning at the wrong boundary, it's gone. Here's a practical version of that. A feature description in documentation is typically a heading, a paragraph, and some structured details underneath. Those elements belong together semantically. Split them across chunk boundaries, which happens easily with naive token count chunking. and you end up with fragments that are technically present in the index but can't be assembled into a useful answer at retrieval time. The right chunking strategy depends on the document type. Now let's take a look at this one. Legal contrast, section-aware segmentation, clauses and subclauses stay together, support threads, conversation-aware grouping, question and resolution in the same chunk, research papers, abstract-aware anchoring. The abstract sets context for everything that follows. Product documentation, heading hierarchy preserved, structure carries meaning. There is no universal chunk size. There is only context-appropriate segmentation. Beyond structure, you're also making decisions about overlap, how much context to repeat across boundaries, whether to use semantic similarity models to determine split points rather than token counts, whether chunk size should vary based on content density. Each of these decisions compounds. The right choices raises your retrieval ceiling. The wrong ones cap it, regardless of what you build on top. Here is the lesson. Chunking is architecture, not preprocessing. Treat it accordingly. With clean, well-segmented content, you move to indexing. Two things here that are commonly misunderstood. The first is embedding versioning. Most teams don't think about this until it causes a problem. You upgrade your embedded model, which you should, as better models become available. And suddenly, your query embeddings and your document embeddings are encoded in different semantic spaces. Retrieval starts degrading, not dramatically, not with any errors, just quietly, in ways that are genuinely difficult to diagnose. That's embedding drift. The fix isn't avoiding model upgrades, it's planning for them. Version your embeddings. Have a clear strategy for reindexing when models change. The second thing is metadata. And this is where I see the biggest gap between demo implementations and production systems. Metadata isn't decoration, it's control infrastructure. Without access level filtering, you surface documents to users who shouldn't see them. Without version filtering, you will confidently retrieve content from a policy updated 6 months ago. Without tenant isolation, you have data exposure risk. Without recency weighting, stale content ranks equally with fresh content. These aren't edge cases. They are categories of failure that shows up in production. And they have real consequences. Your metadata schema deserves as much design attention as your embedding model. Both determine what's findable and what isn't. The lesson here is this. Indexing is representation strategy, not storage. The decision you make here determines what your system is capable of finding and what it will never surface, regardless of how good your retrieval layer is. Retrieval is where most people focus their optimization efforts. It's the most visible layer. It's where failures surface. And is the layer with the most tunable parameters. But there is something important to understand about retrieval before you start tuning it. It can only surface what the layers below it preserved. In my case, I spent several hours adjusting the retrieval parameters. The thresholds, BM25 weights, re-ranking passes. My average query quality improved. The specific failure I was trying to fix didn't move. That's the signal. When you make improvements that lift the average, but don't fix a specific case, the problem is upstream. Retrieval was performing correctly. It just had nothing correct to return. So let's talk about what production retrieval actually looks like. The baseline is hybrid search. Vector similarity handles semantic intent. It finds content that means the same thing as the query, even when the wording is different. BM25 handles lexical precision, exact terms, product names, version numbers, acronyms. Neither alone is sufficient. Together, they cover the space. On top of hybrid search, you add metadata filtering as a hard constraint layer. You are not just finding the most relevant content. You are finding the most relevant content within the boundaries the system is allowed to search. Then re-ranking. A re-ranking model takes your initial results and reorders them by actual relevance. Not just vector similarity, but contextual fit to the specific query. And finally, similarity thresholds. If your best match scores below a threshold, don't return it. A low confidence answer is often worse than no answer. It creates false trust. But the piece that separates a thoughtful retrieval implementation from a basic one is adaptive routing. Not all queries are the same kind of question. Explain how this works is a conceptual question. Get me the Q3 2024 compliance report is an exact match request. What changed in the benefits policy last year requires temporal reasoning. These should not run through identical retrieval logic. Adaptive retrieval means classifying query type and routing it to the appropriate path, each optimized for specific kind of request. The lesson here is this: retrieval is relevance engineering, not search, but it's also the layer that gets blamed for every failure upstream. Before you optimize retrieval, make sure ingestion and chunking aren't the actual source of the problem. Once retrieval is returning the right content, the question becomes, how do you communicate it to the model? And this is the layer most people treat as improvisation, and it's the one that makes the failures hardest to diagnose. Here's why that matters practically. When something degrades, and it will degrade, you need to isolate the variable. Was it the retrieval, the prompt, the model, a data change? If your prompt is undocumented and unversioned, you've removed your ability to answer that question. You are debugging a black box inside a black box. Prompt construction should be deterministic, auditable, and versioned alongside your models. The model sees three things: system instructions, content blocks, and the user's question. The order matters. The structure of each matters. The boundaries between them matter. System instructions define behavior, constraints, and output formats. They should be explicit, not implied. If you want the model to say, "I don't have enough information," rather than guessing, that needs to be in the instructions. Context blocks are where your retrieved chunks go. The order you place them in affects how the model weights them. Retrieved content ordered by relevance produces better outputs than content injected randomly. Token budget management here. How much context you include before coherence starts to degrade is a calibration you run deliberately, not guess at. Overload the context window and coherence degrades at the edges. Leave the instructions ambiguous and the model fills in the gaps with behavior you didn't intend and can't predict. The lesson here is this: your prompt is the interface between your system and a probabilistic engine. It deserves the same engineering discipline as the rest of your stack: version control, documentation, and deliberate design. Everything we've covered so far: ingestion, chunking, indexing, retrieval, prompting, those are the components of the system. Orchestration is how those components come together. 2 dimensions to get right: performance and reliability. On performance, implementations are fully sequential. Embed the query, then search, then re-rank, then generate. Each step waits for the one before it. That's fine in development, but in production, that latency stacks, and the compounding effect at P95 response times is something users feel before you measure it. The question to ask is this: what can run in parallel? Query embedding and document metadata retrieval don't depend on each other. Run them concurrently. Document summary prefetching can start before the retrieval completes. Some re-ranking operations can happen asynchronously. Parallelism reduces perceived latency, and perceived latency is trust. Users don't file tickets about slow responses. They just come back less often. On reliability, production systems need the full set of resilience patterns. Caching for repeated queries, retry logic with exponential backoff, timeout thresholds per component, circuit breakers that fail fast when a dependency is degraded, graceful fallback that gives users something useful when the system can't give them everything. Cold starts deserve specific attention. In demos, no one hits the initialization penalty. In production, new users hit it on the very first request, which is also the very first impression of the system. Have a warm-up strategy. The lesson here is this: orchestration determines whether your system feels reliable. Performance and resilience aren't features you add later. They are architectural decisions that need to be made here. This is the layer that converts a RAG system from an experiment into infrastructure, and is the one most commonly skipped, which is exactly why systems that look fine in staging fall apart in ways that are impossible to diagnose in production. Here is the core insight. Symptoms appear at the output layer. Causes exist everywhere else. In my case, the symptom was a bad retrieval result. The cause was a destroyed ingestion artifact 3 layers below. Without observability into ingestion quality, I was debugging the symptom and never finding the cause. That's why it took several hours. Once I looked at the raw ingested content, it took 4 minutes. Production observability means instrumentation at every layer, not just a response. At ingestion, quality monitoring that flags structurally suspicious chunks, low token counts, encoding anomalies, content that looks like garbled table output rather than coherent text. These are catchable automatically if you are measuring them. At retrieval, full logging of what was returned, in what order, at what similarity stores. This is how you distinguish retrieval returned the wrong thing from retrieval returned nothing, from retrieval returned the right thing, but ranking was wrong. At the prompt layer, capture the full prompt sent to the model, not just the query. When something goes wrong, you need to see exactly what the model received. At the system level, latency breakdown by component, token usage tracking, and drift monitoring. Tracking retrieval quality scores over time, so you catch gradual degradation before users do. Beyond logging, you need evaluation infrastructure. Offline test data sets with known good answers. Controlled queries that don't change, so you can run them after every deployment and detect regression. Human review pipelines for edge cases and novel failure modes. The combination of logging and evaluation is what gives you the ability to know, not guess, whether the system is getting better or worse. Every change you make to any layer becomes measurable. Every degradation becomes diagnosable. Every improvement becomes verifiable. Without that, you are operating on intuition, which works until it doesn't. The lesson here is this: observability is what makes everything else in this stack improvable. Build it first, not last. The cost of retrofitting it is always higher than the cost of building it in. 7 layers, each one solving a failure mode the previous layer created. The gap between a RAG demo and a system that works reliably in production isn't the model, it's the infrastructure that ensures what you think is in the system actually is, and that when something breaks, you'll find it in minutes and not in days. If you found this video helpful, subscribe and leave a like. It helps more than you know. And I want to hear from you. Where has your RAG system failed? Drop it in the comments. Tell me what broke and which layer it came from. Was it ingestion quietly destroying your tables? Chunking splitting meaning at the worst possible boundary? Embedding drift creeping in after a model upgrade? Or were you just like me, tuning Retrieval for several hours while the problem was 3 layers up? Whatever it was, share it, because the most useful thing this community can build together isn't another demo. It's an honest map of where these systems actually break in the real world. See you in the comments.